Welcome to another Win with Math video. Today's video, we have the square root of 1 cubed, which can be simplified to be square root of 1, which is 1. 1 and 1. Square root of 1 cubed plus 2 cubed can be simplified to the square root of 9, which is 3, which can be written as 1 plus 2. 1, 2, 1, 2. Square root of 1 cubed plus 2 cubed plus 3 cubed can be simplified to the square root of 36, which is 6, which can be written as 1 plus 2 plus 3. 1, 2, 3, 1, 2, 3. So you're probably wondering, square root of 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed, does it have something to do with 1, 2, 3, 4? Well, this simplifies to the square root of 100, which is 10, which is in fact 1 plus 2 plus 3 plus 4. 1, 2, 3, 4. So you're probably thinking, oh, is there a general case? Square root of 1 cubed plus 2 cubed plus 3 cubed all the way up to n cubed? Well, 1, 2, 3 all the way up to n, in fact, is equal to 1 plus 2 plus 3 plus all the way up to n. So let's prove that this is true. For our first proof, we'll take a look at this 1 cubed plus 2 cubed plus 3 cubed all the way up to n cubed. This is the sum of cubes, in which it has a nice formula, which is n squared times n plus 1 quantity square over 4. And then we're going to take the square root of this. Square root of n squared is just going to be n. Well, technically it's absolute value of n, but since we know that n is positive, the absolute value becomes a little redundant, so it'll be just positive n. Same way with the square root of n plus 1 quantity square to be n plus 1, and the square root of 4 to be 2. And then on the right hand side, 1 plus 2 plus 3 added all the way to n is the sum of consecutive integers, which is n times n plus 1 all over 2. And here we've proven that these two statements are actually true. For our second proof, we're going to rewrite this to be a formula that we're more familiar with. 1 cubed plus 2 cubed plus 3 cubed all the way to n cubed can be written as the summation from I equals 1 to n of I cubed. And don't forget the square root. And then 1 plus 2 plus 3 added up to n is the summation from I equals 1 to n of I, which we already know is n times n plus 1 over 2. And then we can square both sides to get the more popular formula, the summation from I equals 1 to n of I cubed, which is n times the quantity n plus 1 over 2, the whole thing square. By proving this last formula, we've proven the original statement. So let's prove it. We want to prove that this formula is true for all positive integer n. So let's label our left hand side and right hand side, and then we're going to prove this with mathematical induction. So with the base case, which is n is equal to 1, on the left hand side we'll substitute n equals 1, simplify this, we just get 1 cubed, which is 1. On the right hand side, when we substitute n equals 1, simplify this, we get 1 squared, which is also 1. So we've proven this is true, hence the base case is true. After showing the base case, we need to show that the inductive case is also true. So we're going to assume that this formula is true for all positive integers k. We need to next clearly state what we're trying to prove is true. So we need to show that the summation from I equals 1 of k plus 1 of I cubed, basically we are replacing k with k plus 1. It's in fact equal to k plus 1 times k plus 1 plus 1 over 2, the whole thing, power 2. And the k plus 1 plus 1 is really just k plus 2. So we need to show that this is true. So let's start with the left hand side. So we have summation from I equals 1 to k plus 1 of I cubed. This can be broken down to summation from I equals 1 to k of I cubed plus the k plus 1, the whole thing, to the power of 3. Then, by using our assumption, summation from I equals 1 to k of I cubed is really k times k plus 1 all over 2, the whole thing, power 2. And then we add it to the k plus 1 quantity cube. And then let's move over here. Next, let's use the exponent and expand it out. So we get k squared times k plus 1 quantity square over 4. And then for the k plus 1, the whole thing, power 3, let's break that down to k plus 1 times k plus 1 quantity square. And then if we're going to add these two, we need common denominator of 4. So we're going to multiply this second one by 4 over 4. Now, if we look at both of them, they both have a purple k plus 1 quantity square and a denominator of 4 together. So we're going to factor that out, and that will leave k squared plus 4 times quantity k plus 1, which 4 times quantity k plus 1 is really just 4k plus 4. And k squared plus 4k plus 4 can be simplified to k plus 2 quantity square. in which we can pull out the square, and we're left with what we need to show, which is the right hand side. So we've proven that the inductive case is also true. So in conclusion, what we're trying to prove, summation from I equals 1 to k of I cubed is equal to k times k plus 1 all over 2, the whole thing to the power 2, is true for all positive integers k. Going back to our original problem, this I've shown that the square root of 1 cubed plus 2 cubed plus 3 cubed plus all the way up to n cubed is in fact equal to 1 plus 2 plus 3 plus all the way to n is true. Square both sides, we get this. Or particularly, we can read this as the sum of cubes is really just the sum of integers square. If this video helped, give it a like, subscribe for more, click on the video on screen to keep learning. Thank you.